I got this interesting question from a student the other day, which I wanted to share. It reads, if you double both masses in an Atwood machine, the resulting acceleration will be. First, of course, we need to agree on what exactly is an Atwood machine. So an Atwood machine is comprised of a pulley, which I'll draw out as a circle. We can imagine that this pulley is perfectly frictionless for the sake of our argument here. And the pulley is attached to two ropes, which are attached to two masses. So the two masses are hanging essentially from either side of the pulley. And I'm going to label these masses M1 on the left and M2 on the right. Now, as I'm sure you can already decide pretty much intuitively, if M1 is greater than M2, that our pulley is going to rotate in the counterclockwise direction. It's going to rotate like this. And so for the sake of this question, we'll assume that M1 is bigger than M2, and we'll call the counterclockwise rotation the positive rotation of the pulley. So if M1 is allowed to free fall, that will actually be the positive direction for M1, whereas if M2 is being pulled up, that will be the positive direction for M2. So just to set our bearings correctly, so that when we do our FNet statements from our free body diagrams, we have the positives and negatives sorted out already. That's what we're going to do now. If we draw out M1 and M2, and all of the forces which are acting on them, I'll call this one 1. There is, of course, tension going upwards in 1, and force of gravity going downwards in 1. Now, it's very, very important to say that the force of gravity is acting in the positive direction, which we've shown in red, and that the tension is acting in the negative direction, which we're now going to show in blue. And a way that you can think about this is that the force of gravity is the force which is acting to speed up M1, and that the tension is the force which is acting to slow down M1. When we do our FNet statement, the force of gravity should be a positive value like this, Fg, minus the tension, which is going to be represented as a negative value because it's a force which is acting in the negative direction. Likewise, for block number 2, we've got tension going upwards and the force of gravity going downwards. The difference here is that the force of gravity is acting to slow down our system. It's essentially preventing F2, or block number 2, from going up towards the pulley. Whereas the tension is the force which is pulling block number 2 up towards the pulley. So when we write our FNet statement, our tension should be the first term, which is positive here. And then we should put a negative sign, and then we should put our Fg, which is the second term. Now, when we expand our FNet statement to say MA, it's very important that our M is the total mass, which I'll write as capital M. Whereas our force of gravity for block number 1 is only dependent on the mass of block number 1. So I'm just replacing each of these terms with either M times A for FNet or M1 times G for Fg, because that's specifically the force of gravity acting on block number 1. Now, same thing for block number 2, the total mass times the acceleration is the tension minus M2 times G, just the force of gravity acting on block number 2, which is derived from M2. Now, I can expand my total mass to say M1 plus M2 times A. This should equal M1 times G minus T. And same thing in block number 2, M1 plus M2 times A equals T minus M2 times G. Now I have a series of two equations, and the two equations share something in common. The value that they share in common is the tension. So this T value is the same in either equation. Now I know that because if I go back to my original Atwood setup, it's the same rope which attaches, albeit all the way around the pulley, M1 to M2. And what we know about our massless ropes is that the tension is constant at any point in the rope. Doesn't matter where we are, doesn't matter if we've gone around a pulley, the tension is always constant. So mathematically what I can do is I can isolate each equation for T and then go from there. So for my first equation, if I move T over to the left-hand side and it becomes a positive, and I move this whole term over to the right-hand side, it should become a negative. So T equals M1G, that stayed there, minus M1 plus M2A. From my second equation, it's a little bit easier mathematically. All I have to do is move this negative M2G over to the other side. It's going to become a positive. And when I do that, all of that should equal T. So I'm actually just going to write that as equal to T in the same line as I had before, plus m2g. So all of this came from what I rearranged here. And because it's equal to t, they are equal to each other as well. So all of this is equal to t. Now I have one big equation, which I can try to boil down to answer my question about acceleration. I'm looking for a. And the way that I'm going to answer my question about acceleration is I want to gather all the terms with an acceleration component on one side and all the terms without an acceleration component on the other side. So on the left, I'll leave m1g. It doesn't have an acceleration component. I'm also going to take m2g from the right and subtract it from both sides. It becomes negative m2g on the left. And then on the right-hand side, I started with an m1 plus m2a. And I'm going to add in another m1 plus m2a. Now, these two terms on the right-hand side are identical to each other. So I can basically rewrite this. And in fact, that's what I'm going to do in this exact line as just one term with a coefficient of 2 in front. So 2 m1 plus m2a. I've essentially factored it. Now I can divide both sides by 2 m1 plus m2 just to leave a on its own, m2g over 2 m1 plus m2, and that will leave us a on its own. So now we have a nice formula which describes the acceleration. I'll call this a1. This is for our current setup. So what I want to do with this new equation is I want to explore what's going to happen if I were to double both of the masses. I have a mathematical way of assessing exactly what's going on in the question. I'll call this a2. Now the only difference between a1 and a2 is in the place of m1, I'm going to write 2 times m1 because it got doubled. It was still being multiplied by g, and that was still getting m2 subtracted. But again, that's being doubled. So I'm going to write 2 m2 there times g all over 2. And then again, I'm going to double these guys, 2 m1 in place of m1 and 2 m2 in place of m2. Now, what I hope you notice is that there are a total of 4 terms. That's 1, 2, 3, and 4 in the entire fraction. And that each of our 4 terms has been doubled. We've introduced a 2 in each of those 4 terms. And what I can do is I can simplify my fraction by dividing my numerator and my denominator both by 2. When I do that, I'm essentially canceling out the 2's that I just added in. Because they got added into the numerator and the denominator, my a2 simplifies to read as m1g minus m2g over 2 m1 plus m2. And if this looks familiar to you, that should make pretty good sense because you'll notice that this was the exact same acceleration formula that we had in a1. So a1 is equal to a2. This means that the acceleration before we doubled both masses is exactly equal to the acceleration after we doubled both masses. Going back to actually answer the question, if you double both masses in an Atwood machine, the resulting acceleration will be the same as what it was before. We can choose A.